Swayam Prabha. Digital India. Educated India.
So, after looking through the concrete mix proportioning in the module 4, let us look at module 5, and in this one we will be looking at the concrete process, especially in the fresh state. So, first lecture on this is actually batching and mixing of concrete, and we should be talking about first what is concrete production, the production process, batching and then mixing in this particular lecture. We will follow it up with transporting, placing of concrete and then curing, as the concreting process can be described in this manner. First you have batching, followed by mixing, followed by transport, then place it, compact it, and you of course you will have to cure it. That gives you the concrete. So, this is the concrete production process, and in this process of course, quality control is most important. Finally, the product should be as we desire, as we would like to produce, to our requirement. So, therefore, this is what this diagram shows, the concrete construction or production process. Today of course, we will concentrate ourselves to batching and mixing. Now, what is batching? It is basically the process of measurement of specified quantities of cement, aggregate, water and admixtures. You see, we have decided the proportions in the last module. We have looked into the from the requirement of the properties or performance requirement of concrete. We have tried to find out what should be the relative proportions of different ingredients in concrete, namely cement, cementitious system, aggregate, water and admixtures. Now, batching is the process by which actually we weigh them, we measure them, measure the specified quantities in correct proportion. So, that is what is batching. Now, batching process can be volumetric or mass basis, weight basis. Now, volumetric batching could have been, it was done earlier long back, and even one might do is like one volume with 6 volume, one volume of cement with 6 volume of sand, 1:6 mortar and that kind of thing. So, it is very loose actually. So, volumetric batching in case of concrete is not desired. If you have some container, you can fill in the container with the aggregate, and therefore, volumetric one can measure this volume. So, it was relatively easy or less time consuming, I will say, to just put in some up to in a container, for example, 1 cubic feet box. So, just fill it with the aggregate, and that is volumetric batching. Now, that is not desirable, because controlling the total mass within a volume is very difficult. Somebody may put in little bit more by shaking it, so that it packs better. Somebody may just put it as a heap and just wipe off from the top or travel it from the top. So, we will have less volume of aggregates. So, therefore, volume is difficult to control. So, therefore, engineered concrete is produced on mass basis, and that is what your Indian standard code IS 456:2000 also says. Because mass basis you can reproduce it, loose volume cannot be reproduced and it is not economical. So, loose volume is not reproducible and therefore, it is not economical, except for some small job you would not do it. Then control and storage of materials, you must have aggregate bins for storing aggregates, silos for storing cement and cementitious material. Actually, storing is very important. It should not get, for example, aggregates, they should not get contaminated with dust or something of that kind. Apparently, it may look simple, but if you store it in open, you can have problems of dust coming from the environment and contaminating them, especially places like, let us say, northwest India, where dust storms are quite common in summer, like Rajasthan, even in places like Delhi, Kanpur, you have such kind of dust storms, and storing aggregates in open may be a problem. Even when you have rain in other parts of the country, not the central and the western northern India, rain can bring in a lot of things, dust along with it and deposit over the aggregate. So, therefore, it has to be stored in the right manner, so that it does not get contaminated, aggregate do not get contaminated by dust. Cement, of course, we know that you have to keep it outside away from water. So, they are put in silos, so is fly ash. So, all cementitious material and aggregates are stored as mentioned, and they form part of the batching plant. So, if you look at the components of batching plant, first aggregate bins for various types of aggregate, right. So, they are stored in bins. Then you must have some kind of feeding mechanism, might be scrappers, conveyors or hoist, to transfer the aggregate to the scales, that is to the balance. Now, here there may not be a separate balance, it must be a bucket straight away, where you can go on the mass that is added. We will look at that a little bit more. So, feeding mechanism is the next one. Then you have balance or measuring system for the aggregates particularly, and also the cement. Then you have continuing with the components, cement silos and conveyor screws or bucket conveyor for transporting the cement from the silos, because you got to take it to the balance and then from balance to the mixing machine. Then storage tank for water and water measuring system. If you have admixtures, chemical admixtures, some kind of a dispenser for chemical admixtures, which will actually add to the system before mixing. So, these are the components. Now, let us look at a batching plant straight away. How does it look? This photograph shows a batching plant, and as you can see, these are the silos. In fact, it had twin cement silos and one silo for fly ash. So, these are the silos, vertical silos, where these are metal silos where cements are stored. So, cement will be stored and it is all closed, and from here the cement goes to the mixer machine. So, this is a fly ash silo, as it is shown, two cement silos, one of them you can directly see, the other one is not easily visible. So, this is one cement silo, the other cement silo is there, and fly ash silo is somewhere here. And these are the aggregate bins. So, this is aggregate bin, this is also aggregate bin, right. So, aggregate bin is here and aggregate bin is there, and there is a scrapper which will actually be lifting the aggregates, as we shall be seeing from the photograph taken from the other side. Okay. There is a scrapper. So, this scrapper is the one, this is the scrapper, this is the scrapper. So, this has got this got actually a scraping device which can scrap the aggregate system close to the wall. These are the walls which are there, this is the wall, this you can see, these are the walls. So, this wall there is another bin there. So, this is the wall for the other bin. Every bin has got a scraper. So, scraper would actually lift the aggregate or push the aggregate close to the wall, and at the in the walls there is a gate, there is a gates. So, this gate can open onto the bucket automatically, can be a computer controlled system, and it can just put into the buckets. So, you can see that you can see further now more things in from the other side. The flyer silo is now easily visible. This is the flyer silo, this is one cement silo, other cement silo. So, these are the two cement silos, and as you can see, this is the control room. There is a control room here, this is a control room, this is the control room. So, where you have a computer and through which everything is controlled, and screw conveyors. So, these ones are screw conveyors actually, this particular one. Similarly, there is another screw conveyors through which cements are shifted from the silo to the mixer machine, silo to the mixer machine, and you have got the mixer machine ending up somewhere there. Mixer machine is somewhere here, mixer machine is somewhere there. So, materials are actually, this is the components, this shows actually components of the batching plant. Currently used batching plant in India, these are called star type, and this is fairly common most of the places. Only thing is storage bins of the aggregate could differ from place to place, but basic structure remains more or less similar. So, this is typical batching plant. Plant type of course can be cyclic or continuous. Now, this is what I showed was a cyclic. So, every time the material is weighed and then put into the mixer machine, continuous, it will be continuously fed and weighed. Now, that is a very fast process and rarely used in Indian scenario, unless you want to produce large quantity of concrete at a very short time. So, in a casting yard or something of that kind, not very common in Indian scenario. The other is classification could be automatic or manual. So, what we normally see is the cyclic type, the one I showed. In fact, the continuous type, even the mixing should be continuous. So, it is a continuous feed onto a mixing system, which is cylindrical in nature, and it enters from one side, the ingredients enter from one side of the mixer machine, and it gets discharged from the other side. Now, plant type can also be automatic and manual. This is automatic. Most of the batching plant today with the RMC plants would be automatic. Manual would be weighing, would be manual. Weighing would be done manually. Small batching plant could be manual. What is important is accuracy of weighing. Accuracy of weighing. So, IS 456 says plus minus 2% for the quantity of cement measured. That means, the accuracy should be within plus minus 2%, and 3% from the quantity of aggregate. Water and admixture, quantity of aggregate, water and admixtures that we are measuring. So, accuracy level is 2%, right, and then measurement. Earlier the manual type would be mechanical lever system, but the automatic will have load cells which normally we use in engineering laboratories for measuring the load. For example, if you want to measure the load deflection curve of a beam flexural member, you would have used load cell to measure the load that you have applied. It is nothing, there can be several kind like piezoelectric type, piezo sensing, or electrodynamic type. So, the load that you apply, additional load would actually induce some kind of electrical signals which is amplified, etc., etc. So, these are modern machines will have load cells, mostly piezo type or some cases electrodynamic type, right. So, that would measure the mass, right, and that would usually measure the cumulative mass. So, you have a bucket which is fitted with load cell, and each ingredient, let us say if you add cement in the beginning, then if you add cement, the mass of the cement that is gone would be measured, then you add aggregate to it. So, cumulative mass would normally be measured, not individually in the bucket, and load cell does this. Then discharge from the storage and weigh hoppers is through gates generally. So, these gates are, in case of cement, is the screw conveyors which will bring it, and there must be gates which will get closed down. So, they are actually operated by compressed air cylinders. Similarly, for aggregates, there are gates at the wall that I showed you earlier, and these gates should open, operated by compressed air. So, they will open only when there is a, if the computer control system, the control system says or dictates it to be open. As soon as the required weight or the mass has been loaded onto the bucket, it will get closed. So, they are the automatic type, and this is what is used most of these days, and should be used in engineered concrete. The manual concrete is not really engineered concrete, but a weigh batching can be done manually also, where you have simple lever on which you move the weights, move the some weight into the lever arm of the lever arm, and it will tell you how much weight you have reached. So, it is a kind of analog handling. It is possible, but they are only meant for small sorts of small concreting. In fact, the most of the engineered concrete should be produced only with automatic batching, otherwise your quality may not be very good. If you want better quality control, it is desired that automatic control system should be used, because today you have RMC plants available, but of course, with RMC with appropriate kind of quality control is important, and this RMC truck you can have it in a centralized batching plant. You produce the concrete, batching and mixing plant, you produce the concrete, transport it through ready mixed trucks, as we shall be discussing in our next lecture, and deliver it to the site. So, even relatively smaller quantities can be produced in a mechanized way, especially in most of the towns, most of the capital state capitals have got RMC plants today, and even slightly smaller towns. So, with the transportation system improving, road system improving, it is engineered concrete should largely be produced through automated batching plant rather than manual. However, manual batching plant weighing is done by manual means, right. So, you should preset the desired batch weights, and earlier it was done through punch card or digital switches or rotating dials, but today it would be all through computer control. So, you just put those number in your computer keyboard, and that's it. So, it can be easily done today using automatic control system, all right, and that is what would be the best for the engineered concrete. Moisture gauges, usually electrical resistivity type, but microwave moisture gauges are available, which you just insert onto the aggregate, and it will tell you what is the moisture content, because it is desirable that all the time moisture content of the aggregates are measured and corrections are applied in your mixed proportion, because added moisture will be then less, because some moisture is there in the aggregate, and total aggregate quantity will be more, because aggregate contain moisture. So, if you have SSD condition aggregate, how much quantity you need, you have to adjust depending upon the moisture condition, and therefore, moisture should be measured all the time. Water is most commonly measured through flow meters, although in some plants water can also be weighed. So, flow meters can be used, but you can volumetrically you do measure. This must be regularly calibrated as regulatory routine practice, and sometime you might do even specialist check of the weighing process, because otherwise you can have problem with the quality control. Right kind of proportions you are not giving, you will not get the right kind of properties. So, the system should be such that you should be able to check the calibration without too much difficulty, right. So, that is the batching process. IS 4925 gives you batching tolerances. Many codes or guidelines gives you batching tolerances in elaborate manner, but this is for Indian standard. Cement and other cementitious material, it is plus minus 1%. Batching tolerances, like the tolerance in the measuring system and all that, how much error it can have, it is linked to the accuracy that we talked about. Water by volume or weight is plus minus 1%, and aggregate plus minus 2, admixtures plus minus 3%. And this is meant for 30% of the minimum weight, that is 30% of the scale capacity divided by the weight tolerances given in the previous table. For example, in case of let us say I have a maximum capacity is something like about 1000 kg is a maximum capacity of my weighing machine, weighing system. So, the cement, the tolerance that has been specified in the previous table will be applicable to 0.3 into 1000, which means that 300 kg divided by 1% is the weighing tolerance. So, this should be applicable to 300 kg of the cement, minimum cement. If you have minimum weight, anything above this you can actually apply these tolerances, but anything less than this, these tolerances are not really applicable. So, these tolerances are meant for 30% of the scale capacity dividing by weighing tolerance mentioned earlier, while for aggregate this might be 300 divided by 2. So, 150 kg. So, accuracy required is related to that, actually is tolerances given. So, lesser the tolerance, you should be measuring more, so that the error is less. So, uniform concrete, this is actually required, all this are required. You should always be measuring within tolerances, and tolerance should be low. We should be measuring it as accurately as possible. The reason is, concrete should be as uniform as possible. What is an uniform concrete? The one that exhibits less variation. If the variation of property, let us say strength variation is large, it is not an uniform concrete. If the slump variation is large, it is not an uniform concrete. An uniform concrete will have less variation in properties such as slump, strength, every other properties that you are looking at, air content, aggregate content, and so on and so forth. So, it should be less variable, it should be as uniform as possible. So, if your proportions are varying, that is, your batching is not proper, right? Batching is varying. One time you have put in x quantity of aggregate, next time you put x plus delta x quantity of aggregate. Now, this delta x must be as small as possible. If delta x is large, the variation in the proportions will be large. So, if this proportion variation is large, concrete is unlikely to be very uniform, in its properties also. Now, let us concentrate on two things. One is the cement content and water cement ratio. Then we can understand how it affects. For example, delta C is the errors in cement and water measurements. All right. This will result in higher strength variation, because we know strength is a function of water to cement ratio. I am talking of ordinary Portland cement concrete for the purpose of understanding and explanation. So, proper batching, therefore, if I have less delta C, less delta W, I will have more uniform concrete, less variation in strength, better quality. Quality means less variation. Okay. So, proper batching ensures better quality. Quality should be less variation, strength should not vary. So, if you have, if you desire to provide a concrete of strength, let us say with 35 MPa or 37 MPa, I should be, the concrete I generate or I produce should have the strength 37 MPa plus minus 2 MPa, let us say in one case, another case 37 MPa with plus minus 5 MPa. The later is poorer in terms of quality. 37 plus minus 2, which means that 35 to 39 is better quality, because whatever I have desired, whatever I have wished, I am getting that kind of concrete. Whatever I have promised, I am giving that kind of concrete. I am generating, producing that kind of concrete. 37 minus 5 is 32 and plus 5 42. So, if I am producing concrete from 32 to 42, the quality is relatively poorer, because quality is judged by that variations that you have. Whatever you said, you should be giving this. Well, this has got a lot of implications, otherwise we may be looking at to that sometime later on. So, this is related to proper batching is related to quality. For example, you can see this, quality is related to variation, lower variation better quality, and if your proportion is not maintained well, then you will have poorer quality. More error in measurements introduces lack in quality or makes the quality poor, because the dispersion is more. Let us see, just look at mathematically simple algebra, no problem. For example, if I am looking at change in dW by C, water cement ratio, variation in water cement ratio, I am just calling it a dx. So, x is water cement ratio, dW by C. So, it is a partial derivative, and therefore, it will be given as W by C variation with respect to water multiplied by delta W, plus from basic calculus we understand this, partial derivative of with respect to cement W by C multiplied by delta C. Now, variation of W by C with water will be given by 1 by C into delta W, and variation of W by C, partial derivative of W by C with respect to C is given as minus W divided by C square delta C. So, you see, if this is in my errors in delta W, weighing of water, and this is the error in weighing of cement. For example, W 1 minus W 2 and delta W is the variation in difference in water content, and delta C is the variation in cement content. So, my water cement ratio, higher this value, this water cement ratio will vary more, and strength is a function of water cement ratio. So, higher this value, actually more will be my variation dx, water cement ratio will vary more, and if the water cement ratio vary more, higher variation in delta W by C, if it is high delta W by C, it means higher strength variation also will be higher, right, strength variation will be higher. So, if the strength variation is higher, which means that my mean strength, this is related to actually standard deviation, this should be sigma 2 actually, it is related to standard deviation. In fact, I can show the strength variation will be 1.65 into delta sigma. So, I will have higher delta sigma, strength variation is more, I will have higher delta sigma, strength variation is more, strength varies from lower value to higher value, standard deviation will be more, statistical standard deviation will be more, and therefore, my actual increase in strength or mean strength increase. This is given by for mean strength. Remember, mean strength was target mean strength F m was written as F c k plus 1.65 sigma. So, if the sigma is higher, mean strength will be higher, mean strength in one case is more than that of in other case, and therefore, I might end up actually getting, this is the difference in mean strength delta F m, mean strength variation will be higher if the standard deviation, change in standard deviation is more. So, standard deviation higher, variation in higher standard deviation results in more the standard deviation variation, more will be my strength variation. What all I am trying to point out, you do better weighing, our standard deviation will be lower, and if the standard deviation is lower, my F m will be lower for the same F c k, for the same grade of concrete my F m will be lower, and how much lower, that will be given into k, that is 1.65 into standard deviation difference. So, lower standard deviation is always better, lower standard deviation is always better, lower standard deviation is always better. Okay. Now, feed should be ribbon feed, something like this. This is a good feed, you can see that it is feeding through a conveyor belt. Of course, this is another batching plant, not the earlier one. It is a good feed, feed shows into the bucket, feed to the bucket should be ribbon feed like this, coming almost as a ribbon, and some premixing of the material is good before it comes to the feed. So, this was related to batching, importance of batching. Now, let us look at mixing. It is the process, we produce uniform concrete. So, we have different materials of different specific gravity, different shape, and then we mix them up to produce a kind of uniform cohesive mix. Therefore, I should choose my equipment and method in such a manner that it is capable of effectively mixing concrete material containing largest specified aggregate to produce uniform mixture for lowest slump. It is actually difficult to mix dry material. If it is wet, it is easier to make a cohesive mix out of it. So, lowest slump means least water system, least paste and water system, and I should choose the mixing machine in such a manner that whatever lowest slump material I am going to use or concrete I am going to use, it is able to mix that as uniformly as possible. And larger the size of the aggregate, the size variation is more. If it is paste only two materials, cement and water or cementitious material and water, that is easy to mix. If you have aggregate, it is say sand is relatively difficult to mix. Now, you have three component of three varieties, three sizes, and if it is still coarse aggregate, it is still difficult to mix. So, larger the aggregates, largest aggregate, and it will have a tendency to go away, So, segregate also, large particle has a tendency to fly away. So, it is difficult to mix. So, my mixer machine should be chosen in such a manner that it is able to mix uniformly the lowest slump and aggregate, with maximum size of aggregate. Again, I can have cyclic or batch mixers and continuous mixers. So, cyclic or batch mixers is what is commonly we use, and continuous mixers are used only in very large site where production requirement is very high, capacity has to be very high, and I should be producing continuously. And remember, continuous mixing is much more automated system. In a casting yard where production capacity is extremely high, and I need very sophisticated system for continuous mixing. It is usually cylindrical, comes from one side, the ingredients will come from one side, and rotating cylinder through which it will be mixed, and by the time the ingredients has moved from one end to the other, it is already thoroughly mixed and will be discharged. So, that is a continuous mixture, normally not seen much in Indian scenario, I have not heard of one. But the commonly used mixtures are gravity mixers. So, what they do? They actually bring the material up and then they are forced to go down. So, some kind of forced movement is used for mixing, and the gravity mixers can be tilting or non-tilting type. They are not the very best type, normally tilting type of mixers has been used quite often for small concreting, and largely in Indian scenario before the batching plant, where batching plant is not used, actually use tilting type of mixtures. They are not the best mixtures. Counter flow mixer or open pan type of mixtures are the much better one, and that is what is used in most of the batching plants, right. So, tilting type of mixture will look like this, it will look something like this. So, you have got some baffles here, you will have some baffles here, baffles here, and material is fed in, and it is at inclined shape, the baffle should cause them to move. So, this is baffle should be of different shape, blades, and it actually rotates, all right, it rotates about this axis, it will rotate, and by this rotation up and down also this movement, the mixing is done, and when you want to discharge, you just drop it downward in this direction. So, you tilt it and it is dropped, and that is very commonly used small type mixtures. They do not do a very good job, as I told you. So, they are gravity type of mixture. So, what the baffle does? Baffle lifts up the material, just puts it here and they drop down on their own, and this is how first it will so it by this repeated lifting up material and dropping, it actually causes mixing, and this baffles, and they so it's and then finally discharging is through the tilt. Okay, discharging is through the tilt actually. This is tilting drum. This is exactly the previous one what I talked about. So, it rotates actually, tilting axis about which it can rotate. I mean, this is the rotation axis, this can rotate about this, it rotates in this direction. So, material goes up and down, you feed from here, and when you want to discharge, you tilt it and it will discharge. So, this is the tilting axis, this axis it can actually go like this, whole system can come downwards and discharge. So, this is commonly used mixer for small concreting. This is the process, filling the mixture. When you fill from this top, this can rotate about this, then axis of rotation moves, this is where the mixing occurs, and then finally discharging is through this. So, this is commonly used mixture type, but normal big batching plant, this is non-tilting type actually. Here you charge from here and rotate, it rotates while mixing, a counter rotation would actually cause it to discharge through this one. This is normally closed, then you open it up. So, the counter flow causes or the flow causes this to discharge out. There is of course, the motor or whatever it is, not very commonly used, not very commonly used, not very commonly used. This is the non-tilting type, you feed it, this is closed, and when you want to discharge you can just open this, there is a chute here. So, this is the feed of the material, and that is how actually this is your non-tilting type mixer, not very common. This is what is most common, this is what is most common. So, you have a rotating drum which will rotate, and these are the blades, these are the blades actually, this is the inner blade, this is a smaller blade, outer blade, and this relative motion of the drum and the blades. So, therefore, your concrete is here, here is your concrete, and this rotates about this axis. So, drum can rotate, baffles can remain steady, or drum is steady, baffle rotates, and this causes, this is at extreme periphery, this is at inner side, and this causes the mixing to take place. For example, you can have counter shaft. So, there is a baffle here, right, pan is fixed, this rotates, this rotates, this rotates, right, scrapers, these scrapers are moving. So, this moves. In this one, shaft is at the center, this is also center of the shaft, and this is rotating, drum also is rotating. So, this scraper can be fixed, sorry, in this one drum rotates, scrapers are fixed. In this one dual shaft and scraper moving, this one moves, and drum pan is fixed, this pan is fixed, this is fixed, in this case also this is fixed, in this case pan fixed, scraper is moving. So, here scraper moving, pan fixed, in this one pan rotates, scraper is fixed. In this one pan rotates, scraper also rotates. So, scraper pan rotates, scraper fixed, but the shaft is also rotating. So, this shaft rotates. So, there is a kind of planetary motion, and in this one planetary motion, this one shaft rotates in this manner, and pan of course is fixed. So, you can have different kind of action, but most common type is the one that I showed earlier. A photograph of the same is like this. So, for example, here you can, as you can see in this particular one, the scrapers, this is the scraper, there is a inner scraper which you could have seen before, inner scraper which will look like this. Inside scraper is the inner one, this is the inner one is scraper, and then you have got the scrapers again, outer one, and then finally. So, you have inner scrapers here and scrapers there. This is where the shaft, pan is fixed, in this particular one pan is fixed. So, this is one type scraper, this is other scrapers, the smaller scrapers you can see somewhere up there, this is other scraper, this is the other scraper, this particular one is the other scraper. So, this is the inner scraper is here, this is the inner scraper, this is the inner scraper, this is the inner scraper, all right, this is the inner scraper. So, drum rotates and the pan is fixed here. There are scrapers of the two kind, you can see the bottom of the scraper somewhere there, you can see the bottom of the scraper somewhere there, you see this is the bottom of the scraper, and similar sort of baffles scrapers are there. So, they rotate, they will rotate and scoop the material out, put it in the inner side, and as the rotation continues it mixes from outer to inner one, and these are much more efficient than gravity type of mixers. So, this is the commonly used pen mixers in case of batching plants which are used today. As I told you, continuous mixer is one, usually non-tilting drums with screw type blades rotating in the middle of the drum, and you have feed from one side. Drum might be tilted slightly downwards towards the discharge opening with a slope usually of 15%, and you feed from one side, usually very short mixing time, depends upon slope, useful in low slump pavement concrete. So, if you are producing large quantity of concrete, this might be a useful one. You feed from one side, and then it is a continuous batching also, continuous mixing also, feed from one side, and the screw type of blades that causes the mixing as it rotates, the rotating drum rotates, and then it discharges at the end by the time actually the mixing has been finished. So, the most important thing is the uniformity of the mix. We have seen that batching is also required for uniformity. Now, how do we do uniformity tests? So, we actually take samples of fresh concrete from the mixer at different stages of its discharge from a given batch. For example, either it is in terms of quantity or let us say in terms of time. So, let us say it takes about 2 minutes time to discharge. So, I can take from the first 15% of the discharge 2-minute time uniformly discharging, let us say, right. So, I have got actually 120 minutes, and 15% of that will be 18 minutes, 18 sorry 120 seconds, 2 minutes means 120 seconds. So, I can take from first 18 seconds, I take some concrete and cast samples out of it, test for slump, cast samples, cubes, etc., etc. Similarly, I can take from the another next 15% or next 20%. Now, next 15% would be from 19 to 36 seconds, or I can take from the last 15%, which will be actually 102 minutes to 102 seconds to 120 seconds. So, I can go on taking samples at different time of the discharge, right, and measure their properties, and through this actually I will be able to do uniformity test, and I will actually test several things. I will just talk about that in a minute. Now, charging of the mixer machine should be pre-blending and rebonding effect, which I showed earlier, the feed, and mixing time 1 minute is required for 0.75 meter cube capacity mixer and 0.25 minute required for each additional 0.75 meter cube capacity. This is given as per the code, but we will talk about this a little bit more. Let us just talk about uniformity of the mixing. Typically if you look at feeding, we will look at uniformity, but if you see feeding, first stage is dry mixing. I put in dry mixing, this is time versus solid component in the mixer machine. First I just feed in, during this period I am feeding, and here I am doing a little bit of dry mixing. Then again I am loading, but in this case some water I have loaded, during this period I have loaded the water, and this is somewhat wet mixing. Then I load the final quantity of water and it is total mixing. So, this is your true mixing period, and then this is the discharge period. So, typically first I do a little bit of dry mixing, then add water. So, add the solids, dry mixing, then add water, also some solid, also water, and then finally all are added in this zone, and then total mixing period goes on, and then there is a discharge period. So, this is typically the sequence of mixing or solid component in the mixer machine. So, you can see first I added some solid, no more solid here solid plus water, then this is again some more solid, and then continuous mixing here, and then finally this is the discharge. So, this is how the mixing goes on. Total mixing time looks like this, and IS 4925/1968, previous one 0.75 meter cube, this is in IS 456/2000, but 4925 is elaborate. It says mixing time for each batch of material except the full amount of water, provided that all the mixing water shall be introduced before 1/4 of the mixing time elapsed, shall be 1.5, 2 and 2.5 minutes respectively for mixer capacity up to 2 meter cube, 3 meter cube, 4 meter cube respectively. IS 456 of course is very simple. It says that overall minimum mixing time should be 2 minutes. So, this is the guideline given in the code 14925. The earlier one I gave it from, I think it is some kind of consideration available in literature, 0.75 meter cube a time is given, for additional each 25 0.25 meter cube the additional time is given in the previous slides as we have seen, right, like something like, we can go back, actually we can go back to the previous one, this one mixing time, that is 1 minute for 0.75 meter cube capacity, and for additional 25 meter cube is required for 0.25 minutes is required for each 0.75 meter cube. That means, you have got about 1.5 meter cube will require 1.25 minutes. If you have 2 meter cube, will require about 1.25 plus another 25, that is 1.5 minutes. Whereas, the IS 456 says that nothing less than 2 minutes you should be mixing, which is simple, but then the other one the like the I 4925 tells you 1.5 minutes for 2 meter cube, same as what I said earlier, and for 3 meter cube 2 minutes, and 4 meter cube for 2.5 minutes for 4 meter cube. So, these are the mixing time, but we will see the basis behind all this. But first of all, let us see why I need sufficient time, because increasing the mixing time may result in more uniform distribution of hydration product, because it causes abrasion over the surface of the aggregate, and therefore removes the hydration product, and some of the hydration product then further gets exposed to water. New hydration product would get deposited on top of the aggregates and so on. So, it actually causes a better dispersion and more uniform scenario, and therefore, higher compressive strength. But there is a point of diminishing return. If you go on increasing this, it may not increase the strength proportionally, and sometimes it can even cause decrease. All right. So, there is a limit up to which you can do it, because mixing may cause overgrinding of the material, too much of abrasion between aggregates, and some cases may increase in the proportion of fines if the aggregates are weak. Quite often excessive mixing leads to segregation in case of leaner concretes. So, mixing time should be optimal, not too much high. We will come to this mixing curve a little bit later, but just look at performance of the mixture. I said that you can take from first 15% and last 15% or in between any range, and the variation should be least. So, uniformity of the mix is measured by measuring workability of fresh concrete at different points of the discharge. Then you also measure the density of the fresh concrete, measure the air content of the fresh concrete taken at different point in the discharge, time of discharge. You take from the 12 seconds out of 120 minute, let us say discharge time, let us say is 2 minutes. So, first 12 seconds you take one sample, next 12 seconds take another sample. You can go on taking 10 samples and find out the variation. But if one way is to take from first 15% and last 15%, because at the end it is tendency of aggregate is to come first, they will get discharged first, the paste will come last. So, particularly in tilting type of mixtures, if it is bottom discharge, this problem is much less, it comes out all equally, but tilting type of mixtures, aggregates will come first, paste head has a tendency to come first. So, uniformity can be measured from first 15% of the mix and last 15% of the mix, and variation should not be too much. So, compressive strength of cubes you can measure, coarse aggregate content you can measure by analysis of the fresh concrete. You simply wash it, do wet sieving, put it on a sieve of 4.75 micron size, mm size, 4.75 mm size, put all the concrete, put a water jet, coarse aggregate will be remaining, fine aggregate will go out. So, coarse aggregate content you can measure easily, analysis of fresh concrete, water to powder ratio you can find out, because whatever is going out you can just again put it to a 75 micron sieve, and whatever is remaining on it is the sand, rest is water to powder, and you can actually find out, the analysis of fresh concrete can be done, find out the cement content, water to powder ratio, powder content you can find out by doing analysis of fresh concrete. So, actually what I was talking of, you can have workability, density, air content, compressive strength, coarse aggregate content, water to powder ratio and powder content. Those kind of fresh analysis of fresh concrete done, and you can measure them, and workability and strength can be measured at appropriate time, and then see what is the variation. If the variation is less, you are very happy, it is within a limit. In fact, code specifies the limit, and it also says that to define a mix to be uniform, maybe 5 out of the 6 or 4 out of the 6 or 6 out of the 7 should be satisfied. The various code tells you differently. So, 4925 is quite stringent, it says 6 out of the 7 or I think it is 5 out of the 7 should be satisfied. The ranges are given, how much the variability of workability can vary by how much slump variation is possible, how much density variation is possible, these are given, and number of tests it should satisfied out of this 7 is also specified. I have not actually included this because this would have become too long. So, one can check this, use the code and decides, test the mixer machine to find out whether it is giving you uniform mix or no. Rayleigh criteria of course is something like this. It depends upon what is called coefficient of variation, which is standard deviation from different samples, measurement from different samples divided by the mean. So, you find out coefficient of variation because its standard deviation COV is standard deviation divided by mean. So, you find out mean strength, mean water to powder, and also find out the standard deviation from 10 such samples taken from a single batch. And if the coefficient of variation is less than 66%, you say it is ordinary. If it is less than 5%, then you call performance is very good, I mean just good, and first one is ordinary performance, and high performance is if it is less than 3%. There are several other criteria given, I have just included few of them. Fine aggregate less than 0.25 mm size, fine aggregate less than 0.25 mm size, all right, that is your 250 micron. So, that again the coefficient of variation should be less than 6% to be ordinary, less than 5% and less than 3% it should be, I think there is a mistake there, this should be 3%, it should be high. Similarly, coefficient of variation for dm is the mean particle size and minus dm by 2, mean particle size minus 2. So, proportion of the particle belonging to particular size you find out, and if it is less than 20%, 15%, 10%. Air content, residual air content by mass, if it is less than 2% with a standard deviation less than 1, you call it OK performance. If it is less than 1% and standard deviation is less than 0.5, you call it high. Similar other criteria are given, I have only taken a part of the table. So, therefore, performance are judged from the variation, right. So, more variation means poor performance, less variation means better performance. Uniformity of the mix the mixer machine produces, uniform concrete, less variation, that is a better one. In fact, this should be monitored from time to time in a computer controlled engineered batching plan, because otherwise it does not make sense. You have part of it is computer controlled, if you are not checking routine checking of your mixer machine and batching tolerances and all that, calibration of the batching plan, mixer machine uniformity, this should form the part of the quality control system if you want to produce good concrete, because then only you will have concrete most of the time uniform, right. Otherwise, it will actually introduce standard deviation in the properties. Mixing time I was talking about, we can study this from coefficient of variation. For example, if you look at strength and variance in strength, variance is standard deviation square. So, strength actually increases, but it becomes stable here, does not increase further. Similarly, the variance is nothing but square of the standard deviation. It reduces as you increase the mixing time, but does not actually reduce beyond that. In fact, it might even increase, because your fines might increase. So, therefore, what we see is that there is an optimal mixing time, and uniformity of the mixing is very important. Optimal mixing time, for example, code says 2 minutes. So, preferably 2 minutes, little bit just above 2 minutes is fine, or the guidelines that is given in 4925 or otherwise available in literature, they must be used, but one should not actually prolong the mixing too long. This can result in higher variance and strength. So, higher variation, uniformity will be less, all right, and uniformity test we have discussed. So, this is a aspect of mixing and batching, and they are all related to quality control. Better, if you do a good batching, that means proportions are all the time more or less same, the errors in measurements are less, calibrations are being checked regularly. So, it is within tolerances, the accuracy is within tolerances. That means that proportions, if you are measuring 100 kg, you are batching or weighing machine showing 100 kg, it will be 100 or plus minus 1%. So, say let us say 99 to 101, actually it will be 99 to 101. So, if it is going beyond it much higher, let us say 95 to 105, but you are thinking that it is about 100, it means that it is actually your actual proportion is different. It would lead to more variation in the strength in your final product or more variation in the slump of your final product. So, batching is very, very important, and mixing then is very, very important. Pan mixers are definitely better, and discharge from the bottom is better. Tilting mixtures can cause segregations, because larger particle can go away. Mixing may not be uniform, right. The mixing more uniform, the mixer machine uniformity of the mix that is coming out of the mixer machine should be checked. Important aspect is the time of mixing, type of mixer and time of mixing. Time of mixing too long may not be good, whatever is specified in the code that one may adhere to. So, that way then one can produce good concrete. Quality control is related to both. So, we have looked into the concrete production process, what are the steps involved. Then we have looked into the batching process and its importance in producing good quality concrete, engineered quality concrete, and then we have looked into mixing process for producing uniform quality of concrete. So, that is what has been part of our discussion right now, and with this actually we conclude our discussion.